This is Unit 2, Topic G. We'll begin talking about higher order derivatives. Essentially, a higher order derivative is simply what you get when you differentiate a function more than once. So you take a derivative, and then you take another derivative of that answer, and so forth. We'll start with a little bit of notation. To get a second derivative using Lagrange notation, you simply add more primes. So you could call it y double prime or f double prime of x. You can keep going. We can do a third derivative. Or a fourth or a fifth or whatever. Typically somewhere around the fourth derivative, people stop writing the little primes. It just gets to be hard to count that many little dash marks, and they start using this notation instead. That's a fourth derivative, not a fourth power, when you put the parentheses around it. With Leibniz notation, the second derivative looks like this: d squared y dx squared. You could do the same thing with the function notation here. It would just be d squared and x squared, or third derivative d cubed y dx cubed. I'll sneak in the function notation on this one too. And that one just keeps on going. You don't have to make any changes. It's already about as efficient as it's going to get. Euler notation. D, the derivative of y with respect to x, or the derivative of f with respect to x. This one, you just put the order of the derivative on the d. So d squared y is the second derivative. D cubed y would be the third derivative. And d to the fourth y with respect to x would be the fourth derivative. And then finally Newton. First derivative, again, remember he was typically taking the derivatives with respect to time. Second derivative, he would have just put 2 dots. And although it could be imagined that he probably would have used 3 dots or 4 dots if he'd gone any further, typically first and second derivatives are about all you're going to see using the Newton notation. All right, in our first example, we'd like to find all derivatives of y is equal to x to the fourth minus 6x cubed plus 5x squared. What exactly I mean by all derivatives, I think will become clear as we start doing this problem. So I'll start with my first derivative, 4x cubed minus 18x squared plus 10x. The second derivative, we just use this first derivative and do another derivative on that. So 12x squared minus 36x plus 10. And then we keep on going. Third derivative, take the derivative of the second. So 24x minus 36 plus 0. The fourth derivative would just be 24, the derivative of the 36 becoming 0. And then notice what happens when we get to the fifth derivative. The derivative of that constant is 0, and therefore all remaining derivatives will continue to be 0. So I could say the nth derivative of y is equal to 0 for all n greater than or equal to 5. So if you start with a polynomial, if you take enough derivatives, you'll eventually get 0. Now, of course, that's not true for all types of functions. Consider y is equal to sine x. Y prime would be cosine x. Second derivative would be negative sine x. Third derivative would be negative cosine x. And then when I get to the fourth derivative, I'd have a negative negative or a positive sine x, which actually kind of puts me right back to the beginning again, doesn't it? And then that cycle would just repeat itself. The fifth derivative would be cosine. The sixth derivative would be negative sine x. The seventh derivative would be negative cosine x, etc. So although the derivatives never become zero, they do repeat themselves in a very predictable pattern. Again, that's not always true. Oftentimes, higher order derivatives just get messier as you go along. And for an example of what I mean by that, take a look at this next example. To do even the first derivative of x secant x, I'm going to need a product rule. Let's let f be x, and g would be secant x. So f prime would be 1, and g prime would be secant x tangent x. And so putting in my product rule, fg prime plus gf prime, the first derivative, f prime of x, is fg prime x secant x tangent x plus gf prime, which is just 1 secant x. All right, let's try the second derivative. Once again, when I look at this first term, I'm seeing actually kind of a double product rule here. There's really 3 factors. I'm going to let x secant x be the first, and tangent x be the second. And let's see, this time, I'll let f be x secant x. And I'll let g be tangent x. Now for f prime, I'm going to steal a little bit from myself. X secant x is what I had right here, right, to start with? And when we did its derivative, we already did that whole product rule, and we got all of this. So f prime is actually going to be this whole thing. And g prime, the derivative of tangent x, is secant squared x. So I now need fg prime plus gf prime. Fg prime, x secant x times secant squared x plus gf prime, tangent x times this whole thing. So that's that whole product rule. And then I also have to take the derivative of secant x, which is secant x tangent x. Whew. So you can see what I mean by some of these derivatives don't follow a nice pattern or keep on getting simpler or anything. Some of them just keep getting worse. This would be a good example of that. Let's clean it up just a little bit. I'd have x secant cubed x plus distributing here would give me an x secant x tangent squared x. And then here I'm going to get tangent x secant x. And there's another tangent x secant x, so 2 tangent x secant x. And I think we're going to call that about as good as it's going to get. Thank goodness we didn't ask for the third derivative, right? All right, our primary application of second derivatives is going to be the fact that the second derivative of the position function will give us acceleration. Right? The first derivative is velocity. So if r is position, actually I think we've been using s. If s is position, then s prime, the rate of change of position, would be our velocity. And we're saying now that s double prime is acceleration. Let's think about that for a minute. If the first derivative is velocity, and this is the derivative of that, this is the rate of change of velocity. Well, what do we call the rate of change of velocity? If we change our velocity quickly, we're accelerating fast. If we change our velocity slowly, we're accelerating slowly, right? So the second derivative, the rate of change of velocity, really is acceleration. Let's take a look at an example of a problem where we can use that. If an object is thrown upward from the top of a building and allowed to fall to the ground, the height in feet, t seconds after the object is released, is given by this h of t function. So I used h instead of s, but same idea, right? Find the velocity and acceleration of the object at the instant of impact. Before I even start to worry about velocity and acceleration, let's concentrate on that instant of impact. At the instant of impact, the height will be 0. The object is hitting the ground, right? So if I just set this equal to 0, and again, you can solve that quadratic equation any way you want to. You can use a graph, or you can use a quadratic formula, whatever you want to do. Maybe I'll go ahead and just use a graph this time. Let's see, for my window, won't take that long to fall. Let's go 0 to 10 seconds, probably be enough. As far as the height, even at time 0, it's already at 300, so I'm going to go 0 to 400. See if that'll take care of it. And there we go. And actually, in order to figure out where it crosses, I probably should have gone a bit below that x-axis. The calculator doesn't like to find x-intercepts unless the graph actually crosses the axis. So I want the 0 of the function. And it looks like about 5.757. seconds would be our time of impact. All right, we know what velocity and acceleration at this time. So velocity is s prime, negative 32t plus 40. The velocity at the time, 5.757, would be negative 144.2. And that would be feet per second in the units for this problem. Acceleration is our second derivative. So if I take the derivative of the first derivative, I just get negative 32. And in this case, it's constant. There's nothing to plug in. So it's just negative 32 feet per second squared which should look kind of familiar to you. That's just the constant acceleration of gravity in the American system. All right, that brings us to the end of this nice short topic G.